Hello, folks. Welcome back. Yes, if you're chewing, you can just wave. Yes, far be it from me to interrupt lunch. Yes, indeed. So I've heard several folks talking about homework. Should we start there? Maybe entertain homework questions, maybe do a little reviewing. That's the purpose of this homework. It really hasn't covered anything new. It's the idea of preparing us to do new things starting this class period. One question that I've gotten from lots of you is, when in my estimate statements do I do times 2 and when is it squared, right? Because it seems arbitrary, but it's really not. So I thought I would go over that with you specifically and see if that doesn't help clear up some misconceptions. So here is the most complex model, I believe, that I asked you to estimate from the last section. Let me move this thing over. I'm writing this out just in a simple regression format. This model is not a complete representation of the model because it is disregarding all the variance components. So this is a model for the means specifically. You could even call this like y hat, but I will never use that term for reasons I'm happy to share after class. But we have the fixed linear and fixed quadratic effects of time, as well as the effect of gender on the intercept, education on the intercept, and their interaction on the intercept. And I'm saying on the intercept because these terms right here that I've highlighted don't interact with time. That means they're not predicting a slope, they're predicting the intercept. Whereas these terms here, this is the effect of gender on the slopes for time, linear and quadratic, and this is the effect of education on the linear and quadratic slopes as well. Now, did I ask you to do the four-way interaction in this? Was that mean? There is one? Okay, let me see. Let me read my own instructions here. As well as moderation of the quadratic slope by education and sex by education. Boom. I need to add some stuff. I am that mean. Thank goodness. I thought I was making it easy on you guys. So I'm going to add a whole nother row here. So I'm up to beta 10 here and beta 11. And I'm going to go like that. Right? Now do I have everything? Okay. So let's do an example then. Let me squish this back together. No. I don't want spaces after, thank you. There we go. That's a little easier. So if I were to ask for, say, the education slope for a woman at a particular time period, for instance. So if what I want to know is the ed slope, I need to pull out of this equation everything that has to do with education. So here's one. Not that one, not that one. I need these ones. I'm going to run out of space here. And I need these ones. There. So if I'm estimating the ed slope, I need everything in the model that has to do with the ed slope. None of the terms that don't include education. So if I want the education slope for a woman at the second occasion, even though it's for a woman, the main effect of gender does not go in here because it's the education slope for a woman as the root. So education has to be in everything. So what we're really looking at then is a revised version of beta 4 that reflects all of these interaction terms that modify the effect of education. So if I pull education out, what do we call that in math terms? Am I factoring it out? Is that the right word? Yeah. I'm pretty sure my, no one said pull it out in my junior high math classes or all of us would have giggled. And you giggle, see? We're all just children at heart. but none of you are peeing on the carpet, so that's a plus. 'Cause that's what happens at my house when people giggle. Still working on that whole underwear transition. It's very tricky. See, now I'm giving you time to finish your lunch while we do this. See how nice I am. And one more. Let's move that down. There. Okay. So this is a fairly complex model. It says that what the education slope should be, meaning the number that multiplies it, is a complex function of all this stuff. All this stuff is what forms your estimate statement. So in the syntax, the words that you type, they actually refer to the betas. They refer to the betas that SAS is estimating, and so it fills them in this process. So what it looks like then would be ed1 MW, so I need 1 beta 4, that's ed1, plus if this is the education slope for a woman, I would fill in a 1 here as well. The pluses are implicit here. If I want it at time equals 2, for instance, let's throw in a time 2 here, time 2. So note, when you look at time 2, that's not right. You still have this implicit ed slope sitting in front here. So the estimate statement does not have the education slope factored out, but the logic of it is clearer for what the numbers are if it is. So beta 4 is ed1. Beta 5 times gender is ed times gender with the value that you want the gender for. Beta 8 times time is actually ed times time, and I want it for time 2. How about ed times time times time? Actually, let's make it time 3 because then the math will be clearer. Now, what do I type here? Is this a squared or is this a times 2? This one's the squared. It's the squared time variable that is modifying the education slope. So this one gets a 9. No plus, my bad. And then if I keep going, I need ed by time by gender. That one, I've already given ed the 1, which is right here. I've already given time a 3, and I've already given MW a 1. So 1 times 3 times 1 is 3. Ed times, I did that one last one, ed times time times time times MW. 1 times 9 times 1 is 9. So anytime that time and time squared are moderating a slope of some other variable, that's a squared. Time and time squared are the moderators, and so it is their original and squared values that go in for time. With me so far? Now what if instead I asked for the linear slope at time 3 for a woman with 0 years of education? Let's make that drop, make it a little simpler. So now I'm going time slope. So that's everything involving time. Both time and time squared. Like everything, right? Everything but the main effects of education and gender and the intercept. Now if we go through the same process, subtract out time, factor out time, excuse me, I'll do this a little faster, hopefully, but still not all that fast. There's one time, there's another one, there's another one, and last but not least, there. So when I go to write this statement then, the thing that I need one of is the main effect of time. So there's time gets a 1. Now, this term, time is the moderator. So there is no squared here. This is the times 2. So I write time by time, and if I want it at, what did I say, the third occasion, that gets a 6. Then if I continue, I have time by gender. If I want it for a woman, that gets a 1. Time by gender, that gets a 6, because I've already given gender a 1 here, and I've already given time squared a 6, and so on and so forth. So when you are estimating an effect of time, you will never be squaring time. When you are estimating an effect of anything else, if squared time is a moderator of it, you will be squaring time. Same goes for an intercept. If I ask for a predicted outcome, I'm asking for an estimate statement that looks like this. So the thing that it starts off with is the intercept, the word intercept, and then a 1 behind it. And then you're filling in the values for all of the predictors, including time squared if that is a predictor. So to summarize the rules again, if you are asking for a slope or an intercept of anything but time, and time squared is a moderator of it, you square time in the estimate statement. If you are asking for a slope of time itself, then the quadratic term is whatever time you want it for times 2. Okay, with that being said, any of that you want to hear again, or any questions that you'd like to ask about? Nobody wants to talk? We're all good? You have 2 more days to finish this, and they're all going to turn green. So you'll know that you've got it. Heather. Ah, yes. There's 2 different ways that you can tackle that. Let me find an instance of this. Like these ones up here, 24 and 25. One way is to take what the predicted income is for a man, take that sentence, the predicted income for a woman, because you already calculated those, and you're literally subtracting the 2 estimate statements to see what holds. The other way to think about it is to think about the predicted income difference between men and women. That is the root of the sentence. What term in the model carries the predicted income difference between men and women? What is that in terms of a fixed effect? Not a rhetorical question. What is that? That's the MW term. So you can approach it as take the line that you wrote for the intercept for one person and the intercept for the other person and literally subtract those two sentences. Or you can tackle it directly by thinking about this as the main effect of education and then figuring out what it would be at occasion 1, meaning you would have to have ed by time in the model for that to be different at any occasion, and what it would be for 12 years of education, which is if you had education by gender. I think I misspoke somewhere in there. This is the gender effect. Not in section 1, but hang on. If this is the income difference, yeah, I misspoke. I said the other word. If you have the income difference between men and women, all right, we said that that's the gender main effect. So the next part here, at occasion 1, the only way that that gender difference is going to change over time is if you have gender by time in the model. If you don't, this is the gender difference at 1, at 2, at 3, at 4, at infinity. Likewise, the gender difference for people with 12 years of education, the only way that that's going to be conditional on education is if you have gender by education as a term. If not, it's for any level of education. So some of these later questions that are very simple in the first section start adding terms to them as you add interactions, and that's exactly the patterns that I'm trying to get you to recognize. Okay. Other questions? Now this stuff isn't any fun in the abstract, but it is fun to get to analyze data and meet new people and do cool stuff. So can I tell you a little story to cheer you up? Maybe? Because you all look very sad right now. Like this sucks. Like, I'm not going to argue that it doesn't suck. I will argue that it's necessary. So here's my story and the story behind today's lecture. Once upon a time in 2012, I was checking my email and I got an email from Hawks. Now this may not mean anything to you, but he's like one of the people in multi-level modeling. Like he wrote one of the best-selling books and he's really well known. He's in the Netherlands. And it said, "Dear Lesa, would you like to come to Europe and give a talk on something that you've already talked about and we'll pay you $1,000 and pay all your travel?" Yes, of course I would. My response, "Dear Joop, thank you so much for thinking of me. I'd be delighted to accept this opportunity." So I spent the week after spring break in 2013 going to Paris and then eventually to Utrecht to go for this conference, and it all got paid for, and oh, my husband's tickets got paid for too because they paid me to come and do this. How's that for a good story? See? Learning this stuff gets you places. Now the postscript to this story is how he introduced me when it was my turn to talk. I got to talk first. I was like one of the keynote people, you know. It was so exciting that this person like knew anything about me at all. It's one of those like, wow, like you know who I am? Holy shit, you're Hawks. He's a very, very nice man, by the way. But you are often, at least I've often heard in academia, that teaching doesn't matter, right? It's all about the research. No one's ever going to get tenured on their teaching. You can be the crappiest teacher ever, and as long as you're productive, someone will hire you, right? These are the messages you get. And for somebody like me, it's very disheartening. Because quite frankly, you guys and all of your predecessors and all of your future versions of you, this is why I have this job. This is why I get out of bed in the morning, other than the toddler who's currently yelling at me. But before he came along, this is why I got out of bed in the morning. I get really excited trying to get people to do better science through math and being able to communicate that and learn more in the process. That's all great, right? And I don't want to be told that this doesn't matter. So, Hawks, do you know how he found out who the heck I am? He had to teach a course on longitudinal models a few years ago, so he asked the Google, "Can I find some class notes on longitudinal?" Guess whose website popped up? And he liked my stuff. I don't think he used it or anything, but he liked it so much that he thought of me to come to his conference, and he paid me to come. So teaching does matter, damn it. I got a free trip to Europe. Again. I had already been to Sweden twice for teaching, and I've been to Australia for free for teaching as well. So, it's sin. A, teaching matters. B, if you learn this stuff, somebody will pay you. That's my thesis statement here. Somebody will pay you. Even if you're not a methodologist per se, if you are a clinical psychologist or a sociologist or a measurement person and you are very competent at these models, people will pay you within your discipline. It is a huge boon to be able to say that you can do this stuff. So please, when you're like throwing things at your computer because you can't get it to turn green, keep that in the back of your mind, that this is a valuable skill set. It will make your research better and it will hopefully make your life better as well. But yeah, true story. So this is a talk that I had originally given as an invited talk at a conference in Maryland, and this is an updated version of it that I gave several years ago. And so I thought I would give this in lieu of a more traditional lecture so that you could see kind of how I would talk about these things amongst my peers. The example that we have is close to the data that show up in chapter 10. That's the reading that goes with this. It's not going to be exact because I've gone through so many permutations with this particular data set of examples for this talk, for the book, and for this handout that I have for you. Don't try to match the numbers, but the gist of it's the same. The idea of how do you think about time and why that matters. So, ready? So this is new stuff. It's still longitudinal, but it's longitudinal with an extra level of complexity, sufficiently complex that UPOX wanted me to come talk about it. So thank you, UP. So I will skip some of this because a lot of this was introductory material. I wanted to make the point that there's all these ways people have organized longitudinal analysis, and they all have these same common steps. We talk about intra-class correlation as the first step. You guys know that one. I've deliberately skipped number 2 here, by the way. That's foreshadowing. Number 3 here, trying to figure out what kind of fixed effects of time that you need, what kind of random effects to go with them. We have some options here for different kinds of change. You guys know the first 3. I think I've mentioned 4 in passing before, latent basis models. That's done in a factor analytic context in which you estimate the factor loadings for some of the time occasions to try and approximate nonlinearity. It's a good trick when you have very few occasions, but they need to be bendy and you don't have quite enough, or you don't want to have a quadratic. Step 4 would be predicting inter-individual differences in change. Step 5 would be predicting intra-individual variation, and then there's some extra stuff going on here. Multivariate relationships broadly construed, so things like lead lag or cross lag analyses, mediation analyses. A whole bunch of people at the conferences where I was were talking about mixtures and other kinds of underlying heterogeneity. Just as an aside, we're not going to do growth mixture modeling in this class because that's all bullshit. I'm happy to tell you more about that why if you care, but we're not doing that. It's an exploratory approach that everyone can be right about. So here was my focus here, the missing step 2. This is the part that I would argue comes before all of that stuff. So the goal of any of these processes, these analyses here, is to try and describe change over time. But that phrase in and of itself assumes that we know what time should be. So this missing step here is really 2 different questions here. What should time be when you have multiple choices? And given those multiple choices, how do you model time when people differ in that time? So we're talking specifically about what are called accelerated longitudinal designs. So these are the kinds of studies depicted here graphically. They go by lots of names, an overlapping cohort design, sequential cohort design, not Alex, damn it, Andrew. What do you guys call your design that you have with the kids from the nearby schools? Yeah, cohort sequential, overlapping cohort, accelerated longitudinal, all of these terms kind of mean the same thing. The idea is that you get people at the beginning who differ in the time metric you're interested in, such as age or grade, and then you follow each of them for some short amount of time. So for instance, I might sample people who are 50 to 85 if I wanted to study adulthood development. I measure each of them for 10 years. With the idea that together I can approximate a trajectory that is, 45 years long without actually having anyone in the study for 45 years. That's the idea behind these studies, is that you can get a longer term set of information than any one individual can give you. So that presupposes then that the time metric that you're sampling in this way is meaningful with respect to change. So the example that I have here in the world that I kind of grew up on thinking about these ideas is cognitive aging. Is it the fact that you're aging that is responsible for any kind of cognitive or physiological decline? Or if you could somehow control for health declines, would you live forever in terms of cognition and physical health? So is it disease? Is it normative? It's actually responsible for changes over the passage of time. But all of these questions then about which process it should be, they're not relevant within persons. They're only relevant between persons. So if I think of myself on the planet as an aging individual, for every year that passes, I'm a year older, I'm a year closer to death, I'm a year further in my career, I've been a mother for another year. You can think of any other time metric, all of it within persons is the same. It's just time. It only matters which it should be if you think about the way people differ from each other, which is between and not within. So how do we model this idea that some people are further along in time when the study starts, and yet still respect the fact that time is within persons as well? So these concerns apply specifically when we have between person differences and within person differences in the time variable. So for example, I have data from an octogenarian twin study of aging. You may have heard me talk about this example before. I have data from 173 persons who have known dates of birth and known dates of death. They also have estimated dates of a dementia diagnosis. So everyone within this subsample has been diagnosed with dementia at some point. There's 3 different kinds represented. And at baseline, at the first occasion, here is the correlation between years on the planet, years to death, and dementia. So death and dementia are related at 0.52, but the others are not. So it's not necessarily that the people who are older in the sample are more likely to die sooner. So there's 3 different time metrics that we're looking at. At the first occasion, they range from about 80 to 100 in years of age, from about -16 to 0 years from death. And yes, there were instances of people who died like a few days after their first occasion. And from anywhere from -12 to 18 years past diagnosis, which means some people were already diagnosed when they started the study. Some people didn't get diagnosed until about 12 years later. And I have 3 different measures that I'm looking at to give as an example. One is mini mental status, which is a very generic, fairly crappy measure that's used to screen for dementia. And so it's somewhat tautological in that the dementia diagnosis is predicated on that DV going down. We also have a measure of memory and a measure of block design, which is spatial reasoning. So in considering these different time metrics, I have computed for each of them an interclass correlation. So we talk about interclass correlation, right? Comes from an empty model, normally an empty model for the outcome that you're interested in. But you can take that same machinery and reverse engineer it to figure out how much of your time predictor is between persons if you stick time on the model line as an outcome. So an empty model predicting time. Not useful theoretically, but useful descriptively to try and figure out how much of your variation is actually longitudinal. So for instance, in this sample, age at the beginning, age as time, so just remind you, they were about 20 years different at the beginning, and they were measured 5 occasions over 8 years, about every 2 years. Age is actually about half and half. So half of the variation in age in our sample is cross-sectional, and about half of it is longitudinal. That means, at a minimum, age has 2 different roles to play in the model. Years to death is about 1/4 between and 3/4 within. Years to dementia diagnosis is mostly between, and years in study, as expected, is 0. So all within. So this is the only metric of time that's purely within. And time, as in time in study, that's what we've been doing in every example that you've seen thus far for this reason. Whenever we have time as a predictor in our examples, it's an instance in which everybody is measured over the same time frame. So it's either perfectly balanced or nearly so, such that there are no differences between persons in time. That means that time as a predictor is purely level 1. Therefore, the only possible effect that it can have is purely within. The other time metrics are going to have some of both. They are part between and part within. That means we have to build our models differently as a result. Okay. With me so far? Okay. So here's some pictures. And I have some code that shows you how I made these pictures, but I did so in SAS. And the heavy black line in each of these pictures shows the sample mean that's estimated from a saturated means model, and the individual trajectories then are for different people. And the x-axis is each of the different time metrics that we could possibly fit to the same data. So this is the mini mental status exam. We have years since birth on the top left, which is age. And what I want to point out here is the mismatch between what the sample means suggest, which is sort of a semi-gradual but linear trajectory, versus what it looks like at the individual level. Do you see these little slopies in here? They're much steeper. It's like each person gets to a point and then they fall down. Where that point is differs along age, but the actual age-related change, just staring at this picture, looks a lot less gradual than what this mean line would entail. We have years to death, which is a slightly better match, but still the mean line looks more gradual than what the individual trajectories look like. This one here in the bottom left is as close as you're going to get in real data to an answer key. That's because this outcome, mini mental status exam, is used to diagnose dementia. So in this case, it's like, oh, we're fine, we're fine, we're fine, we're fine, uh-oh. All of a sudden we start seeing a downward shift, and that's the point at which people say, okay, there's something going on, and you have more testing. And after that, things go down, things go badly. But this picture suggests that that time metric would be most appropriate because what the sample is doing in the aggregate and what the individuals are doing is aligned. Whereas the top pictures, there's less of an agreement. That looks like it's potentially more of a problem. Years in study, we still see the same sort of mismatch. The only benefit to using this information is that it is agnostic as to what the theory is behind change. All we're doing is saying, where were you relative to where you started? Not relative to other people at the same age or the same dementia point or the same distance from death, but just relative to where you started. Where are you now? And we're tracking change that way. So the other pictures have somewhat of a similar gist. This one is not quite as obvious as the previous one here, but this is sort of the rightest answer that you would see in real data. Same thing with block design. So then we get into equations. Now, side note, this was a methods conference. It was a conference about multi-level modeling. So no one would have come unless they were either interested in it or experienced with it. And so for that reason, I'm okay with showing equations. Not every audience, though, is going to want to see an equation. Most won't, in fact. But here is the type of equations that you're used to seeing from me. Note that I have words here along with the symbols. That way you don't even have to be familiar with this notation to be able to track it. But the idea is to show what the models look like then when you are fitting each of these time metrics. So I have age as time as the first one, meaning the level 1 model is specified in terms of distance from birth, and this is a time varying variable. So age is level 1 here. I've centered it at 84, which was near the middle at the beginning. And from there, we specify fixed and random effects as usual, where the fixed effects here describe the sample average and the trajectory, intercept, slope at the centering point 84, And note, half the rate of change in change per year, twice the quadratic is how the linear rate of change changes, and individual deviations therein. So this seems okay, right? We can throw in age as time, but this model makes a really strict, untested assumption, which is known as age convergence. It's the idea that the cross-sectional and the longitudinal effects of age are the same. That we're talking about the effect of being 1 year older, and it doesn't matter if you were 1 year older to begin with or you became 1 year older during the study. So the idea is that these effects of cross-sectional age differences and longitudinal age changes would converge onto the same trajectory. Or said more simply, that younger people and older people differ only by age and for no other reason. This is not likely to be the case the larger the age range is at the beginning and to the greater extent that you have cohort differences and selection effects. So to put this in more colloquial terms, have I told you guys about Mimi? No? No? Okay. So I tell these stories repeatedly, so I try not to repeat myself too much. But my last standing relative, my last standing grandparent was Mimi. She died when she was 90, about 5 or 6 years ago. And I used to use her as an example of this problem, because if I think about that original design where I have older people sampled and I have younger people sampled and we're trying to align them all onto the same trajectory, if that's accurate, I should be able to look at Mimi at 90 and be like, that's what 90 is going to look like for me. Except, if you look at what Mimi's life was like when she was, say, 35 and when I was 35, she had given birth to 7 children by then. I didn't have any. She graduated high school but never went to college. I was tenured. She had never held a job outside the home. And up until about age 80 or so, had never worn pants. She was from a generation where women wore skirts, and that was that. She tried to teach me how to sew. It did not go well, but she tried. And I remember one time, she lived in St. Joe, which is off of I-29 going down here. You know St. Joe, Missouri? Yes, I was born there. And I stopped by to visit her the winter of my first year of graduate school at KU, and on the way back from Christmas break. And somehow I mentioned off the cuff that, you know, my mom had made all these cookies, but that she didn't make the window panes, and I really like the window panes. Do you know what window pane cookies are? They're like colored marshmallows that have been like rolled in this like chocolate coconut glue, and they're like balls of goodness. Right, and so I made this offhand comment to her, went back home, and 2 days later in the mail, a shoebox full of window panes showed up from Mimi. So that's Mimi, right? She's great. I'm gonna get a little teary-eyed here because I miss her, but she's a great example of this, right? This is why just being older isn't the same, right? What does older look like for someone from Mimi's generation versus our generation? My son can use the iPad better than me at this point, right? What is he going to look like at 35 or 40 or however? So these sorts of changes that have nothing to do with age but make people look different even when they are the same age from each other, those are cohort effects. And to the extent that you're trying to link together large differences in cohorts, these types of models are going to fail. So we see this a lot in the world of cognitive aging because real old people are hard to get a hold of. And so people tend to go younger and younger in order to be able to have a bigger and bigger sample and measure fewer and fewer. But the result of that sampling is that it's more a cross-sectional study than a longitudinal study. So you have to be aware of how much of the variation in what you're calling time in a longitudinal study is actually longitudinal. In this study, it's half and half, for instance. And we can't ignore that problem. So how do we test if it's acceptable to say that the effect of cross-sectional age is the same as the longitudinal effect of age? It turns into an omitted variable problem. The language here is a little bit tricky, but the logic is that we're going to put in a covariate for when it was you were a certain age. If the trajectories align onto a single trajectory like you want, then it shouldn't matter when you were a certain age. If it does matter, then you have age non-convergence. So it looks like this. We keep the same level 1 model of time-varying age, in this case linear and quadratic, but we augment the level 2 model with another version of age that is time invariant. So here, this is the age at the beginning of the study, centered at the same place. So our reference person changes to somebody who was 84 at the beginning of the study, specifically. Our reference growth curve is the growth curve for somebody when they start the study at 84. And these terms in the middle here then describe the alterations to the growth curve that need to happen for people who started at older ages instead. So if those age time invariant effects are significant, then it matters when you were 84, not just that you were 84. That an 84-year-old from 2005 is not the same as an 84-year-old from 2010, for instance. That's what that means. Here's what it looks like in pictures when this happens. So this plot on the left is the predicted trajectory from the age convergence model, from the model only looking at linear and quadratic effects of time varying age. That single trajectory is meant to somehow capture the entire sample, even though some of the people started when they were 80 and some of the people started all the way at this end. The predicted trajectory from this previous model that controls for age differences and when they started, it looks like that. So I have a predicted trajectory for someone who started at 80, and I have a predicted trajectory for somebody who started at 86. And they differ both in intercept and in slope. So this is a little tricky to wrap your heads around because the intercept in this model is not time zero anymore. It's the particular age that the level 1 variable is centered at, which is 84. So when I say there's both intercept and slope effects, you can see the slope effects here, right? The person who started later is predicted to have a steeper rate of decline than the person who started at an earlier age. But the intercept effect is actually this vertical difference right here if you were to extrapolate backwards into what the later person's 84-year-old measurement would have looked like. Because that's what these models force you to do. They force you to extrapolate to what the data would have looked like before you got there and after you got there, because that data is based on different people. So what it looks like is the people who started the study later, meaning that they were 86 when they walked in the door instead of 80, they were actually predicted to do better at age 84. Now that sounds backwards. Older people were going to do better at the same age? Now think of it from a random assignment selection point of view. Who's still around to participate in research at 86? And has the time and energy and inclination to do so? Any guesses? People who are doing well, right? So what happened to the 80-year-olds who are doing less well by the time they hit 86? They're not in the study. They may not even be on Earth anymore. It's unclear. But the people who are still around to start later are not a random subset. They are an increasingly select group of people who have the health, cognition, and physical ability to get to a research study, right? Just physically getting there, being able to drive, being able to walk all the way back to wherever the testing is. These are issues of mobility that are very significant. Even if you're cognitively doing well, you may not have the physical capability to participate in research. But point being, yeah, because These are not the same people. We cannot link them onto the same trajectory. And they're not a random subset of each other. They are selectively different. So in this context, these sorts of age cohort effects are very, very common. Here's the other outcome. It looks like a gradual decline in memory. Nope. It's a different rate of decline before and after. Here's a block design, same story. In this case, it looks like there's a slightly greater slope in the older cohort, but that they would have been doing better. So is this always a problem? The good news is that it's always testable if it's a problem. You throw in some kind of representation for your between person variance and age and see if it matters. Now there's multiple ways to do that. In this context, I chose to use age at the beginning because that approximated cohort differences in age. Alternatively, I've seen people do something like take the mean age in a study. So if I had somebody who started at 80, and then we measured them at 82, 84, 86, 88. It kills me that Excel's function, by the way, is average and not mean. I almost always forget that. Their average age is 84. Now what if I had somebody who also started at 80, they came at 82, they came at 84, and then we never heard back from them? What's their average age? 82. So this is why I didn't do mean age, because mean age is a function of not only cohort, meaning the year you were born, but also how much missing data you had. And I didn't want to intermingle those two. So I picked years on the Earth at the beginning as my indicator of between person differences. That's why I did it that way. So these are kind of the worst case scenario because of the context of the study. It may or may not be that bad. So I'm going to call on not Alexander again, Andrew. And you're overlapping cohort study, right? So you have how many grades at the beginning? I know you have this complicated diagram I've seen before. I'm going to try and reconstruct the highlights of. Third, fourth, and fifth graders. Okay. Yeah, I'm not going to hold you responsible. There's a lot of different ways to approach this problem, right? But even in the simplest version of what you're saying, right? The bold ones are where you started, and then you measured each cohort until they went to some other school. And now you're saying you got some more data for them, so that's good. So the question then is, do you think of your data this way, where we have third, fourth, and fifth graders, and then we have them all at time 0. Time 0, 0, and then we have time 1. Actually, they have time 2. These guys only have 0 and 1, and this one only has 0. So this is what the design would look like from a time and study perspective, where you could align people by a common 0, meaning this is when you walked in the door, and then you measure change from that point forward within each cohort, or you could align them based on the top, which is their grade level. So you could center the model and look at, say, 4 as the centering point, and you could talk about change across grades, knowing that only certain people contribute at certain grades. So then the question is, like, in this element here, Are all 5th graders alike? Would you expect something different in, what are we doing? Bullying, victimization, meanness, all that stuff? Yeah. Not like academic things, but like socially things. Okay, I get to be a social psychologist today. Hooray. I haven't been that one yet. So bullying, victimization, right? Are all 5th graders equally shitty? Well, I mean, like from year to year, right? Would you expect the 2003 5th graders to be markedly different from the 2004 5th graders from the 2005 5th graders? When you're at the same school system, right? Ugh. So like in this type of design, unless something else happened, let's say that this cohort of kids right here, let's say that in this year, the school implemented a brand new Don't Be Shitty campaign. And they're trying to improve bullying and victimization and other kinds of shitty behavior. Then being in 5th grade might look different after the campaign if the campaign is indeed successful. Right? So it would be a mistake to try to just put in the model what grade you're in and not when you were in that grade. Are you with me? So broadly construed here, the problem is that what we've been used to thinking about as time is both between and within. So we've got to build the between part into the model the same way we put the within part in. The question then is, what the heck does the model mean when you do it this way? So we can do these sorts of age-based models where this is time varying age at level 1 and time invariant age at level 2. We can also use years to death or years to dementia diagnosis because they function the same way. There are between person differences and within person differences in each of these time metrics, and the extent to which their level on each of these variables at the beginning is a significant contributor indicates some kind of cohort difference. There's less of that with these two time metrics. So here's what it looks like once you control for cohort effects and you plot out the predicted trajectory decline in these variables where we have years to death, where this is the eventual ending here. This is a pretty good approximation. It suggests there's little variation between people, that what you're going to look like at the dementia diagnosis point or say 6 years to death, there's a lot more commonality there than what we saw in the age-based model, suggesting that maybe these are closer to the right answer. Same thing in object recall, almost perfect overlap of these trajectories. Spatial reasoning, and so forth. So you can compare models by fit. So here's a review here. If you want to compare the fit of models that differ in fixed effects, could I have done that in REML? That's my patented give the answer away inflection. Could I have compared model fit for models that differ in fixed effects in REML? No, REML doesn't care about your fixed effects. It only cares about your variance model. So for that reason, I did maximum likelihood. And these are the AIC and BIC values. Could I have done some kind of likelihood ratio test to compare whether the age model is better than the dementia model, say? You're shaking your head, Jihong? Why? You're right. Different covariates, yeah, these are non-nested models. We don't see these all that often, but if you're interested in what I would call like predictor wars, like does this set of predictors work better than this other set? That's a non-nested model comparison. Do you remember what the rule is from AIC and BIC? Smaller better or bigger better? Smaller. So which color model wins here? Purple. Yes, the dementia models appear to have the best fit relative to the three. We can also look at the differences across these models and their variance components. Now note, residual variance, not that different. Intercept variance, very different. This is foreshadowing. Remember what I said about within persons, time is time? You're 1 year older, you're 1 year closer to kicking the button, you're 1 year further and whatever. Within persons, residual variance is reflecting differences within persons, right? These models are basically equivalent within persons. The only thing that they would differ in is how well the trajectory is captured by the linear or quadratic trends. And for that reason, they're all pretty much the same. But intercept variance is very different between models. Intercept variance is capturing between person differences at a given point in time. And it looks like there's a lot more variability among people at the same age than there is amongst people at the same dementia diagnosis point, for instance. The populations are more heterogeneous in the non-age time metrics. And then you can also just look, right? Here's the age model versus the years to dementia model. It's model fit statistics support these pictures. So this is where my take on this sort of diverges from the people who trained me. What about just time? So given that you're trying to differentiate between person and within person effects, rather than putting in both age and time invariant age, what if you just made time as the within person variable directly? Then you could more easily split up these two effects. And this is equivalent to something we're going to talk about next week called person or group mean centering. And it actually works out that these models are equivalent in their fixed effects, or they can be made equivalent, but they're a lot easier to interpret. So by the way, here's another trick. I have been burned by PowerPoint animation like so many times I can't even count. Like you go through these slides and you make everything perfect, and then whoever's laptop you're using has a different version of PowerPoint than you, and it doesn't work, and then you look stupid because your things are like flying in at all the wrong times. To counteract that, I make animation through slides. So here's one slide, here's the next slide, here's the next slide. So it looks like animation, but it's safer. And that's why you have like these things in front of you that look like it's like pieces. So the story that goes with this. So what if I have a vector of ages that looks like this here? And what I'm talking about then is differentiating the between person information from the within person as brand new variables. So if I use between person as when you started the study, let's say this person started at 80, this person started at 80, this person started at 84, and so on, I then subtract what they are at each age from where they started. So this is just how many years you've been in the study as the yellow column here. You can do the same thing with years to death. Use where you were at baseline as the between person variable, and you can subtract from the time varying variable to get that. Now, do you see something in common with these yellow columns? Yeah. All of these different ways of thinking about change, aging, dementia progression, terminal decline as it's called when you talk about years to death, all of them are equivalent within persons. Within persons, they are all the same. So why not just have within person time directly, and then let these time metrics fight it out between persons to see which one matters more. So then the model looks like this. Rather than doing this age-based model, where age at each occasion is what goes in at level 1, I am putting in a new version that is how old you are now minus how old you were at the beginning. In other words, I'm putting this yellow column in at level 1, and that's time instead. I still have age at the beginning as my between person variable in level 2. But now these coefficients have a much more direct interpretation. So if I look at, these are my fixed effects. Gamma 0, 0, that's my intercept at time 0. Gamma 1, 0, that's my rate of change. So this is the effect of getting older. I can then see how the effect of where you are at time 0 and how much you change because you're getting older varies as a function of your cohort. So the effect of age at time 1 is the effect of being older when you walk in the door. That's both age, that's cohort, that's non-random selection, that's everything. That's cross-sectional effect of age. The level 1 model then gives you directly the longitudinal effect. So they have a clear interpretation relative to each other. You can do the same thing. I have this whole section here, by the way. This is a giant suck it reviewer 3 for someone in the field who now has dementia, and so it would be very poor taste if I started railing on them. But it was because there was a paper in which me and some of our co-authors were criticized about putting time in the model instead of age, because developmental theory is not about time, it should be about age. And so these slides are my FU to that person, because it is algebraically equivalent. So one theory can't be wrong and the other right if they give you the exact same model predictions, folks. So here's my algebra. One model can be rearranged into giving you the parameters of the other if you have a simple model with just a linear slope. The same thing is true if you allow the age variable to predict the slope. The same thing is true if you allow quadratics, and so forth. So because all of these time models have in common the time part, I've come down on the side that that's what level 1 should always be, just time. It turns out that the only way that these models would differ from each other at the level 1 specification is what kind of random effects that you get back. Here's the math that talks about why that happens. That's in chapter 10 as well. And there is some, I'm not going to call it research, anecdotes from a book, basically. I did a simulation that's in here that talks about the same thing, that suggests that a time-based model, a within-person centering, gives you better random effect variances than an age-based model. It's not conclusive. It's something that I did once, and I haven't bothered to publish because once I found that out, I was not interested in the topic anymore. But here's some stuff about that. So yeah, that's basically all I wanted to say about that. Point of the story. When do you need to care about any of this? Can you tell me? When does any of this matter? No one knows. For what kind of longitudinal designs do I need to be concerned about what time should be and how to address these sorts of challenges? Not all of them. Not all of them. Only some of them. Time is both between and within. So if you have a sample of people who all are sampled at the same times, you're good. Like if not Alex had started with a group of 3rd graders and measured them for 8 years, he's fine, because they're all 3rd graders, right? Now that being said, how old are 3rd graders, not Alex? 8 or 9? Could they be 7 if they're super smart? Could they be 10 if they're less gifted? Right? Do you think that some of your constructs, such as beating the crap out of your peers, might be different if you're 7 than if you're 10? So in that case, you still kind of have to worry about this because your age at the beginning of the study is a moderator. Not all 3rd graders are alike. Now I know actual Heather has to worry about this. We were talking about this morning with Fragile X, right? You talk about wave or period 6 or period 7. So the design of the Fragile X study, how old were the participants at the very beginning? 11 years or months? So all of the children were between 11 months and 36 months, and then you're following them however so often. About every 18 months. Okay. So you have to worry about this. Because is a kid who gets tested by your team at 36 months going to look the same as a kid who's been part of the study for 3 years and now is 36 months? No. Maybe, right? It's an empirical question. So you have to worry about this. See, who else can I pick on? Let's see, Kelsey, you do eating disorder stuff, right? So how long somebody has had anorexia or bulimia or something versus how old they are physically versus how many times they've been in rehab versus, right, all that stuff, you have to worry about this. Who else wants to worry with me? No? Can I tell you another quick story and then let you go? Then we'll look at the example next time. So tenure people have to worry about this. So this came up as a real world issue that there really isn't a good answer for. When you go up for tenure, it's typically in your 5th, 6th, or 7th year on the job. And you're supposed to have your productivity up to that point evaluated. Now the question is, from when do they start counting? Is it everything you've done like in your career up to that point? Or is it since you started that particular job or job equivalent? The year that I went up for tenure in my department in psychology at Nebraska, there were 4 of us going up at the same time. One had come there straight out of grad school. 2 of us had had 2 to 3 year postdocs. One person had had a 5-year K award and a postdoc, and then had come. So as you might guess, our publication and grant records looked different as a function of the fact that some of us had been doing this for 20 years and the others had been doing it for 10, right? So how do you judge our tenure worthiness on an equivalent standard that way? Should we all look like the person who'd been doing it for 20 years? Or should he not get credit for any of the things he did before he started at Nebraska? Like, would that be fair? Well, no, because what do you think got him the job in the first place? All the stuff you had done before then. And trust me, nobody wants a clean slate when you start your first job. You worked so hard to get it. No one's going to want to say, okay, wipe that board back down to 0. We're starting over again. Things no one wants to hear. So it is tricky when you think about how to judge change over time when people differ in where they start. What is time? In that case, fortunately, all 4 of us got tenure, but it was hotly contested as to what the standard should be, and should there be a different tenure standard for somebody who came there straight out of grad school versus somebody who came with more experience? Would that be fair? I mean, this is kind of a rhetorical question, but what do you think? Like, on the face of it, no, everybody should have the same standard, but it doesn't work that way. And it's kind of because of this stuff, right? When people differ in time, measuring someone's progress over time gets tricky. And that's my thesis statement for today. It's tricky. So we will show you how to do these models next time, and then for homework 2, you'll get to do them. Yay! It's actually good because it's more of a review, because it's fitting growth models again, and it's adding age as a time invariant predictor. So these are concepts you already know, just trying to keep track of what age means when it's in the model in 2 different roles. That's the tricky. So office hours start now. I will see you all next week. Let me know if you need help with homework 1.